Periodic battery testing helps determine when and what kind of maintenance a battery needs. It helps verify the physical condition of a battery, its state of charge, and its ability to operate when needed. This first part of the program will look at voltage and resistance testing. The key points that will be covered include the purpose of and basic steps for checking cell voltages and intercell connection resistances. We'll start with the cell voltage tests. A cell voltage test is one way to determine if each cell in a battery is being adequately and uniformly charged. IEEE Standard 450 recommends checking pilot cell voltage once a month and all cell voltages at least once per quarter. IEEE stands for the Institute of Electrical and Electronics Engineers. Standards established by the IEEE are completely voluntary, although they're universally accepted and applied. Standard 450 also recommends that cell voltages should be checked with the battery charger in the float charge mode. The voltages are tested using an accurate calibrated voltmeter, such as this digital volt ohm meter. The volt ohm meter is set to the DC volt position. The meter used here automatically selects the appropriate voltage range. These cells are lead calcium, and on float charge should test at about 2.2 volts. The voltage is read to the hundredths of a volt and recorded. As usual, all required safety precautions should be observed. Since voltage testing involves contacting cell terminals, extra care should be taken to not short across terminals. The recorded cell voltages can be evaluated in several ways to identify possible problems. One way is to identify the highest and lowest cell voltages and determine the difference between them. The difference is compared to high and low cell voltage differences from previous tests. If there's a noticeable increase in the differences, an equalizing charge may be needed to raise the voltage of the weaker cells. Another way to evaluate cell voltages is to determine the average cell voltage. Then each cell voltage is compared to the average. Any cell that's below the average by a specified amount should be noted. The acceptable variation from the average is typically specified by manufacturer or company standards. Here, any cell that's 5/100ths of a volt or more below the average will be noted. A third way to evaluate cell voltages is to compare them to a critical voltage. IEEE Standard 450 states that prolonged operation of cells below 2.13 volts can reduce the life of the cells. IEEE Standard 450 also states that a cell voltage of 2.07 volts or below indicates internal cell problems and that the cell may need to be replaced. Low cell voltages by themselves do not necessarily indicate a problem with the cells. They do indicate that the cells have been insufficiently charged, which can happen for a number of reasons. For example, a low float voltage setting may not provide adequate charging current for slightly weaker but still good cells. Cell voltages can also be low because of higher than normal electrolyte temperatures. Higher temperatures increase the internal discharge of a cell and result in lower cell voltage. Higher than normal temperatures may be caused by internal shorting. If this is the case, the cell should be replaced. But higher cell temperature is often caused by outside sources, such as direct sunlight and space heaters. Steps should be taken to minimize the effect of outside sources. Another cause of low cell voltages may be poor intercell connections. Poor connections increase resistance and reduce current flow in the battery. With reduced current flow, weaker cells may not become fully charged and, as a result, will have lower voltages. The resistance from a poor connection can also cause heating. Excessive heating of high resistance connections can melt the terminals. In extreme cases, poor connections can cause battery fires that destroy the battery and threaten the loss of the substation. Poor intercell connections are sometimes evident by visible corrosion at the terminals. But a terminal connection can look good and still not be good. One way to check the connection is with resistance testing. Connection resistance is commonly measured using a micro-ohm meter. A recommended practice is to connect one probe of the micro-ohm meter to the positive terminal of a cell and the other probe to the negative terminal of the adjacent cell. This micro-ohm meter applies a 25 amp test current across the intercell connector and electronically calculates the resistance. It's a good practice to start taking resistance readings at one end of the battery and work toward the other end. Each micro-ohm resistance reading is recorded. Normal resistances can vary with the size of the battery. According to IEEE standard 484, a resistance reading for a new installation is suspect if the connection has a resistance that's 10% or 5 microohms higher than the average resistance for each type of connection. An example of a type of connection is all intercell connections. Another type is all inter-tier connections. For existing batteries, a connection is suspect if its resistance is 20% higher than the average that was established when the battery was first installed and tested. Or a connection is suspect if its resistance exceeds a manufacturer or company recommended limit. Intercell connections with unacceptable resistance should be cleaned, tightened, and retested. If the resistance is still unacceptable, the cell might need to be disconnected from the battery so that the connections can be disassembled and given a more thorough cleaning. As shown in this part of the program, intercell connection resistance testing helps identify poor connections. Voltage testing was shown to help identify cells that aren't being adequately charged. This part of the program also showed a number of possible causes of low voltages and high resistances. Voltage and resistance tests are two of several tests that are helpful in checking the condition of substation batteries. Another useful test is a specific gravity test. Specific gravity testing will be described in the next part of this program.